Yeah.
Okay, well, welcome everybody. We organized this course since I knew there was a lot of, well, first because I was interested in understanding this and I thought Antony could explain it to me. But then I realized probably a lot of people are interested. So we organized this course in person and online. A brief introduction: Antony is currently a postdoc at UIUC. Previously, he was a postdoc at Perimeter Institute. And previous to that, he was actually a graduate student here in Maryland. Another brief thing about the meeting: since we have a lot of participants, we don't want random questions during the lecture. So we've got two people that are monitoring the question and answer tab on the Zoom. So please, if you'd like to ask a question, post it on the question and answer. If it's a short enough question to write the question, you could just write it. And then one of our monitors can read it if it's a good time for the question. Or if it's a long question, they could ask you to unmute yourself. Otherwise, please keep yourself muted. And at the end of the lecture, we have time set aside for more questions and discussion. So if your question is of the kind that it would be better to wait till then, the monitor may just not activate it in the middle of the lecture. Is there anything else I'm supposed to say? I don't think so. If there is, I'll speak up. So Antony, thank you very much for coming.
Okay, yeah, so first of all, thanks a lot to Ted and Maryland Center for Fundamental Physics for organizing this. Yeah, so I'm pretty excited about some of these recent ideas in von Neumann algebras and gravity, and so hopefully this will be a good experience where we can go over some of the background and some of the new developments. Okay, yeah, and so like Ted said, for the people online, just go ahead and type questions if you need them, and then people here also, please feel free to ask me something if I say something and you've been always wondering something about it. So
So somebody just asked if the recordings will be posted online.
Oh yeah.
Yeah. So we're planning on posting these online. I think we can send an email out to the email list when they go up, but hopefully that'll be a pretty quick turnaround. Okay, yeah, so as the title says, I'm going to be talking about gravitational algebras and generalized entropy. So just to give a bit of a motivation for where we're trying to go with this set of lectures, really we're trying to understand this generalized entropy. So let's start with the formula for generalized entropy. You always write it as a sum of two terms, where this area is, you'd say you take some codimension 2 surface in space-time. You think of this as being associated with some causal development of a 4D region in space-time, and this area is something you would associate with this codimension 2 surface. So in 4 dimensions, this is like a two-dimensional surface. And so generalized entropy is an important quantity that comes up a lot in semi-classical quantum gravity. It goes back all the way to the beginning of black hole thermodynamics, and this is really the context in which it was introduced. This was the discussions of Bekenstein, who was trying to understand what happens to the second law when you throw matter into a black hole. It seems like you could reduce the entropy of the universe by just throwing things into a black hole. And the solution was, if you interpret this as the matter outside of the black hole, if you add the area of the black hole to the entropy and consider the sum total as the total entropy that you're considering, this seemed to be sufficient to rescue the second law of thermodynamics. So this generalized entropy, which is the sum of two terms, is supposed to always increase outside of the black hole horizon. So in that context, this area is the horizon area. But then, people have slowly understood that this quantity is useful for more generic subregions in semi-classical gravity. So you can draw random regions in space-time and try to think about what the generalized entropy means. One reason it's useful is that it's generally expected to be a UP finite quantity. And that's interesting because this entanglement entropy here is the entanglement entropy of quantum fields in the subregion of spacetime. And that is well known to have UV divergences in it. But there's an argument that, the structure of those UV divergences match against similar divergences that show up in this term from, loop effects that renormalize the Newton's constant. And so there's something like an area law divergence here. There's an area and a renormalization of Newton's constant here. And there's various arguments for saying that those divergences match in such a way that this quantity is independent of some UV cutoff. So that's super interesting, and it's what makes things like the generalized entropy well defined. It makes you think that this is really counting some notion of the number of degrees of freedom in a region of space-time or associated with the black hole. But the other thing that's interesting, well, it sort of motivates the fact that it's UV finite, is maybe there's a manifestly finite description of it. And so since you have a quantity that doesn't actually depend on the UV cutoff, maybe it's something that you can formulate directly in the continuum. And so I would say some of the recent works on von Neumann algebras and gravity are trying to give a way of understanding this manifestly UV finite description of the generalized entropy. And so, yeah, just to give a brief background on where some of these ideas have come from, the more recent stuff originally came from these works by Leuthäuser and Liu. We're looking at holography and large N limits in holography, and they were interpreting these large N limits in terms of algebras, and they found these things called type 3 von Neumann algebras, and they interpreted this as a signature of a black hole horizon forming in the bulk description. And then there was some very interesting work by Witten, and then also follow-up work with
Region Drive and Page Branch Drive.
it's a
What?
yeah, that's not from here. I don't know.
No.
Try to okay. Anyways,
Mute.
Now writing.
can you try to mute it?
Region Drive and Page Branch Drive.
Sounds like automated voice.
Oh, someone is giving that.
He's driving.
Yeah.
All
Region
participants,
Drive at Xfinity Center.
mute yourselves.
You might not know
Now
that.
You're not able to mute it, or
You can't.
We can find out.
Drive at Xfinity Center.
Taking this class while driving.
I'll just mute everybody.
mute all
Yeah.
participants.
Just mute everybody.
Okay, sorry, we'll try to keep going. Yeah, so then there was some works by Witten, Chandrasekaran, Pennington, and Longo, who's considered sort of gravitational corrections to this algebra that Leuthäuser and Liu constructed, and they were thinking about it in different contexts that wasn't necessarily restricted to holography. And they argued that the gravitational corrections change the story in sort of a qualitative way, such that you get finite entropies, and those entropies agree in a certain semiclassical limit with this generalized entropy. And so then you can start saying, can you do this? Those were restricted to very symmetric setups, but then you can say, can you do this more generally and start really giving an algebraic interpretation of this generalized entropy formula. So the goal is to try to explain the background for understanding that and to argue, sort of go over how you would construct these algebras, show that there is a generalized entropy, and okay, hopefully go over some applications of this once you have this description. Okay, and so the basic plan for the lectures, I wanted to start with some background on von Neumann algebras because it's a very well established subject, but it also has a reputation of being somewhat technical, and it's on certain, I would say a large number of physicists don't actually know some of the details behind it. So I wanted to go over some of what it means, these statements like this algebra is type 2 or type 3, and try to dispel some maybe misconceptions on why these are interesting or not. Okay, so the first lecture or two will be talking about von Neumann algebra backgrounds, and then we'll be going over how they show up in quantum field theory. And from there, we'll do a lecture or so on constraints in gravity and how that interplays with the algebraic description. And we want to conclude by kind of putting everything together to go over how you construct these gravitational algebras. Okay. Now that we've done that, here, I'll just go to the second board for now. So we're going to start with just an intro to von Neumann algebras. Okay, so one thing to start out with is sort of why would you even begin considering a von Neumann algebra? What is it supposed to be doing for you? And one take on what a von Neumann algebra is it's a way to describe subsystems. So you want to be describing subsystems in quantum mechanics and quantum field theory. And you should think of it as capturing, say, quantum information theoretic aspects of the subsystem. So in particular, you're asking questions that are somewhat model independent, so they don't necessarily depend on the detailed dynamics of the system, but you're asking quantum information questions like, what are the entropies of my system, sort of what are density matrices, things like that. So anytime you're dealing with subsystems, you want to understand sort of the information that just comes from the fact that you're doing quantum mechanics and you're working with operators acting on a Hilbert space. I don't know. Sorry, I'll try to ignore it, but yeah, we can try to get muted. Okay, yeah, and so just to emphasize that last point, a von Neumann algebra, it's always going to show up, occurs as an algebra of operators acting on a Hilbert space. So in particular, they're always like a concrete algebra in that sense. There are abstract characterizations of these, but basically for everything we're doing in this course, you always want to think of there being a Hilbert space involved. You're always working with operators acting on the Hilbert space. Okay. So just to give a flavor of what these are, I just want to start with kind of the simplest possible example. And we're going to consider yeah, is there a way to do a mute everyone? I don't know.
I think there's some glitch, like I keep muting and then it just yeah, mute the same person and mute like a second later.
Okay. Maybe you take on if it keeps happening.
You send them a message.
Okay. Okay, so the example is the simplest possible example where we want to do a 2-qubit system. Okay, so we have a Hilbert space. It's going to be the tensor product of just two by two-dimensional Hilbert spaces. You have a basis ij where I and j is 0 and 1. Okay. And let's say that our subsystem consists of the
Hi, the speaker got muted. Sorry.
Anthony, I don't know if you can hear me, but you're still muted. We cannot hear you.
Okay,
All right,
okay.
can you hear us
I
now?
think you should be able to hear me now. Please send a message if there's any other technical difficulties, but maybe refrain from unmuting. Okay, sorry, so we're doing this 2-qubit system. We want to consider, okay, we have two Hilbert spaces. These are both two-dimensional Hilbert spaces. And we want to consider the system that's just consists of the X operator and the Z operator acting on the first system. So then what you do is you want to construct a system that's independent of these operators. And so you will construct the commutants, and this is just going to be, this is the commutant. And this is all operators commuting with A0. Okay? And so what is this? You can pretty quickly convince yourself that these are just operators that act as the identity on the first qubit, and then it's any operator, any 2x2 operator acting on the second qubit that will obviously commute with these things here. So that is sort of the system that's independent of our system of interest. And then the full von Neumann algebra of the system that we're dealing with, generated by this guy, comes from all of the operators that commute with this commutant here. So we would say that A, which is equal to the commutant of the independent system, is the von Neumann algebra generated by A0. And this consists of all operators acting on the first qubit, like that. So some takeaways, so then you would call this the von Neumann algebra. This is a von Neumann algebra. So there's some takeaways that we can immediately see from this example. So the first point is that A, which was this double commutant, is bigger than the original system. So we see that A contains the original system. But in this case, it's actually bigger because, for example, we added the spin Y, the spin in the Y direction. So the Y1 operator is in A, but Y1 was not in A0. The second point is that this is an algebra. In particular, if A is in A and B is in A, then AB is in A. And this is true even though our original set did not close under taking products, because you can get Y by taking products of X and Z. And the final thing to note is that A0 prime is already, so it satisfies, oh yeah, sorry. So the important thing, the important thing is that A double prime, so if we do this operation of taking double commutants again, you don't get anything new after you've done this procedure once. And this is actually the defining condition of a von Neumann algebra. And I think you should think of this as sort of a completeness condition. It's saying that you have all of the operators that you should have associated with the subsystem. And so you want to keep in mind that this is what it means to be a von Neumann algebra. And then the final comment was that A0 prime is equal to A0 triple prime automatically. So that means, so commutants of any set of operator, at least if your set's closed under taking stars, so you should call this maybe a star set, so it's closed under adjoints, is a von Neumann algebra. So this is actually a useful thing to have in mind. If you have some set of operators and you say, I want to take all the operators that commute with this set, whatever it was, the thing that you get is already a von Neumann algebra. So commutants of anything are von Neumann algebras. Okay. So just to state the definition, sort of mentioned it just here. So the definition of a von Neumann algebra is that it's some star sub algebra of B of H. So this just is the notation of bounded operators acting on a Hilbert space. That statement becomes significant in infinite dimensions, but it just means operators in finite dimensions. So satisfying that it's closed under taking double commutants. So again, you have the Hilbert space already, so you can talk about operators that commute with it. And if it's equal to its own double commutant, you call that a von Neumann algebra. So it's worth mentioning, even though we're not going to be doing too much, we're going to try to avoid too much topology discussion at all in this course. But the famous theorem of von Neumann is this double commutant theorem. Or I forget what people call, yeah, the double commutation theorem. That it says this condition that something is equal to its own double commutant is equivalent to A being a star. Well, we already said A is a subalgebra, but it means that A is also closed in the weak operator topology. And so this is just the topology that you get by taking matrix elements of operators. So you can define it, so A here is an operator, and you define a topology that makes sure the maps to the matrix elements of the operator are continuous maps. That generates this weak topology, and saying that this system is closed, so it contains all limits in this weak topology, is equivalent to satisfying this double commutant theorem. So the final thing that's important, there's a distinction. So when you try to classify all possible, yeah, by the way, if you guys have questions, just kind of raise your hand. So yeah, in general, math people were interested, and for physicists as well, it's useful to understand a classification. And the first thing that you can do is restrict to what's known as factors. And so a factor is just, so a factor should make you think of tensor factor, but it's anytime the algebra and its commutant is just the identity. So basically they have a trivial intersection. That means that your algebra is a factor. And so in our example of the two qubits, we found that we had all of the operators acting on the first qubit was A, all of the operators acting on the second qubit was A prime. So that was an example where we had a factor. So there was no overlap except for the identity operator. So if you're interested, you could modify that construction. I guess I'll just say this. If you modify that assumption where A0, if you take A0, so maybe an exercise, if you take A0 to just be the X operator, and go through that exercise, you'll find an algebra that's not actually a factor. So in that case, you'll find that there's an overlap between A and its complement, and you can kind of see that you can put it in a form where it's sort of a sum of block diagonal operators. Okay. So something that's important, so in general, we're going to be restricting attention to factors since there's kind of a whole story. So by the way, this intersection is called the center of the algebra. So a factor is one where the center, which is the overlap between the algebra and the commutant, is trivial. And so we'll be restricting to factors in most of the discussion of this course. Okay, so if we continue to ask the question of what can you get for factors of von Neumann algebras, the first point that's worth keeping in mind is that for finite dimensions, your factors are just always come as all of the matrices act. Oh yeah, sorry. Go ahead.
Are you always going to restrict to unidal algebras as well, ones that include the identity?
Yeah, von Neumann algebras, I think always include the identity because you take this double commutant and you'll add the identity.
Yeah,
Right.
it commutes at everything.
Yeah, so the identity commutes with everything. So if you take a double commutant, it'll show up. So yes, yeah, von Neumann algebras have identity in it.
Sure.
Okay.
Anthony,
Yes.
there's a question. The last line of the previous board. Does it apply to any set or any set that's closed under star operator?
It's star, yeah, so it's a star subset. So you have to take a set that also contains all the adjoints of the operators as well. If you're working with Hermitian operators and then linear spans of those, that'll always be satisfied. So that's why it worked for our original setup. We had X and Z were Hermitian. Okay, yeah, so in finite dimensions, factors always isomorphic to just the set of all n by n matrices acting, so complex n by n matrices. The reason that you don't get, so if you're familiar with other types of algebras, say like Lie algebras or things like that, there's a very interesting classification. It's not just the dimension that classifies it. It's important to keep in mind that the reason you kind of get everything is actually comes from the fact that these algebras are associative. So usually the interesting algebras, they will do something where they'll drop an assumption like that, but you're not taking commutators, for example, you're just taking products of operators. That's an associative operation, and that tends to generate kind of everything in the algebra in finite dimensions. So it's that on top of this, double commutant theorem. Okay, so something that we're going to be interested in, because we're going to be talking about different kinds of factors in this course, is we want to understand this, this sort of famous classification of factors for von Neumann algebras. So for this, one way to think about this classification is that it's pretty useful to focus on properties of traces. Focus on properties of traces defined on the algebra. So Okay, so just to review, what is a trace? So a trace is a linear functional, a positive linear functional on your algebra that satisfies this tracial property that trace of AB, these are two operators, is equal to trace of BA. So this is kind of the central property of the trace. You can call this the tracial property. And yeah, so it's sort of operators commute inside of expectation values in the trace. So this is the normal cyclicity of the trace. So for example,
And it's always valued in the complex numbers.
yeah, so this is, sorry, so trace sends your algebra to complex numbers. Yeah. It's also, yeah, I think I'll say this. I mentioned this in words, it's also positive. So what does that mean? It says, it sends positive operators to the positive reverse. So it's sort of, it's almost a state on the algebra, except it might, in general, it can send some operators to infinity. Or it can say some operators will have infinite trace. So just so you have this in mind, the standard Hilbert space trace, where you say trace of A is just sum over an orthonormal basis. Like this is a trace. Okay, so that's worth keeping in mind. And so what's going to happen is that there's various different notions of traces that show up for some of these other algebras. They're essentially, you know, sometimes show up as sort of rescaled versions of this Hilbert space trace in a certain sense. But in general, we don't want to say that this is the only thing we're going to do. We just want to focus on this purely algebraic condition and see what kinds of things you can have on a von Neumann algebra. And the classification of types essentially boils down to the types of traces that you're going to have.
Anthony, two
Yes.
things. One is I assume that trace is a linear operator on the algebra.
Yes,
And the other is somebody just asked, could you define positive operators?
yes, I should have done that. Was I going to do that? Let me do that right now while I'm explaining some properties that you might say for the trace. So one thing is that you can demand that the trace is faithful, which means that trace of A is never zero if, if A is a positive operator. And so now I'll tell you what that is. If A is positive. And so recall that positive operators is one that satisfies basically that it always has a positive expectation value or zero. So there's a class of operators in any algebra. This condition is for all psi. So this condition that it always has positive expectation values and invariant conditions. And so these are an important class of operators in a von Neumann algebra. And you want your trace to make sure that it always assigns a positive number to these operators that always have positive expectation value. Okay, the second condition that you often require of a trace these are sort of more technical conditions that are necessary to get kind of a uniqueness result for your traces. So a second condition is known as semi-finiteness. So the trace isn't required to be finite on all operators. If you think of the standard Hilbert space trace in infinite dimensions and you take trace of the identity, hopefully you'll find that that's infinity. And so it's okay for it to be infinite, but you want that the sort of the subset of finite trace operators generate A. So you basically have enough, the trace is finite on enough operators that if you just take those operators and kind of take the subset of those and take a double commutant, you'll actually get all of the operators of the algebra. So you can kind of realize anything as a limit of finite trace operators. And the third condition that's also a technical condition is known as normal. And this is a sort of continuity condition. And so it says that, let me write the condition and explain the words. Is there a question or? Oh, no. That trace of sup an equals the supremum trace of an. So say you have like a sequence, an increasing sequence of operators, an, so these are like positive operators, and you have an increasing sequence of them, and you take sort of the operator that bounds all of those and take the trace, that should be the same thing as the limiting value of the trace of these guys. I'm not going to focus too much on this because this is important when you prove things about von Neumann algebras, but often in computations you're fairly safe assuming that this is, if you have a sensible trace, that this property is going to be satisfied. So the important thing about this is for factors, if you have a trace that satisfies these three conditions, so it's semi-finite normal and faithful. Faithful just means you're not setting things to zero that you shouldn't set to zero. Then the trace on a factor is unique if it satisfies that up to an overall rescaling. So I'll write that as a faithful semi-finite normal trace on a factor is unique up to rescaling. So rescaling is I'm not going to mess with this condition if I just multiply it by a positive number here. For the Hilbert space trace, you normally normalize it so that, you know, the 1D projectors have trace 1, but you can always rescale it so that, say, the trace of the identity at finite dimensions has trace 1, and that's just an overall constant of 1/d. So for some of the algebras, there's not a natural normalization for the trace, so it's kind of important to allow for this rescaling.
Anthony, somebody asked about or commented the trace of self-adjoint operators being a real number. Is that included in what you said, or is it?
Self-adjoint. You have to be a little careful. So positive operators are self-adjoint, and so those will have this positivity condition. And then yeah, as long as you're not doing things like doing infinity minus infinity, then if you write a self-adjoint operator as a difference of two positive operators, you'll get a real number there as well. But it's not part of the, I think it probably just follows from this condition. So yeah, this is the key. Okay, so what I said was if a factor admits one of these faithful semi-finite normal traces, it's unique up to rescaling. And so you can basically classify the factors by classifying the types of traces or the possible values that your trace can take on the algebra. And so this is one way to view the type classification of factors. Okay, so we're going to be talking about projections in particular. So projection. This is just an operator that satisfies e squared equals e, and it's self-adjoint equals e. And again, this is like, for example, you know, the 1D projectors are examples of things that you should be familiar with from quantum mechanics, but they're in general, all projections are not always going to look like that. And so what values can trace of EV for projections in your von Neumann algebras? So the first thing is that you could have trace of E equals 1 up to N. With N element of natural numbers, or you could have it be infinity as well. So if it basically it takes on an equally spaced discrete set of values. So here we're picking a normalization so that it goes from 1 to N, not like 1 over N to 1. So if you check all of the projections in your von Neumann algebras and you find this is the case, this is what we call a type 1 von Neumann algebra. And these are just the standard finite dimensional n by n matrices. And the case of infinity is where you have all of the operators acting on an infinite dimensional Hilbert space. So you normally want to think of infinity is the harmonic oscillator from quantum mechanics. So you should be familiar working with infinite dimensional Hilbert spaces when you do quantum mechanics, and that Hilbert space, if you consider all operators acting on it, is a type 1 infinity. So these algebras, you call it, you give it a subclassification where this n tells you it's kind of the largest value the trace can take.
In this classification that you're setting up, are we assuming that they're faithful, semi-finite and normal?
Yeah, so this is for so we have this.
Can you repeat the question, because it might not.
Oh, sorry, yeah, just so the question was, are we assuming this is faithful semi-finite normal? Yes, so you say factors have an essentially unique faithful semi-finite normal trace, and then we're going to look at that and see what values it can take, and that leads to this classification. Yeah.
How do you define soup of operators?
So these are like positive operators. So you would say an operator A is bigger than B if A minus B is positive. And so there's kind of a natural order on positive operators, and then you have this partial order on operators, and you take supremas in that partial order.
So somebody asks, is this classification only for the von Neumann algebras or only factors?
This is the classification for, I'm describing the classification. So the question, yeah, I don't know if I'll repeat it. Is this true for all von Neumann algebras or factors? I think, so the way it works is you can do a classification of factors using the types, and then you decompose an arbitrary von Neumann algebra, which might have a center, into basically a sum of factors of each type. That's called the central decomposition of the algebra. And so a general von Neumann algebra will look like a sum of factors of, in principle, different types. Okay. So, okay, that was the type 1 case. The second thing that could happen is that trace of E takes on the values from, say, all values, all real numbers between 0 and 1. And so again, we're picking a normalization where 1's the maximal value of this trace. This we call the type 2-1 case. So yeah, in general, this type 2 will mean that it can take on a continuum of values, and then the subscript 1 means that it has a maximum value. The third thing that could happen, I just kind of alluded to it, it could be 0 to infinity, and it can include infinity. So this is known as the type 2 infinity case. And maybe it's worth pointing out the way you distinguish these two is you can just take trace of the identity. In this case, it'll be 1. In this case, it'll be infinity. That'll distinguish between those two types.
1 because we can just rescale it in order.
Yeah, that's just notation. And so these sub classifications, these numbers down here will mean different things in the different types. So just take them always as a definition. Here it was this number. Here, okay, it kind of corresponds to the maximal value, but in the type 3 case, there's another number that has nothing to do with these traces. Because the last thing that happens is that you could have trace of E essentially is always infinite. So unless the operator is 0, it's gonna be infinity. And in this case, this is known as the type 3 case. And actually, okay, so maybe technically what this means is this trace is not semi-finite. So what you would actually say is there is no faithful semi-finite normal trace for these type 3 algebras.
There's a question of whether this is really a property of the algebra or if it depends on which trace you choose on the algebra.
So the answer is it's a property of the algebra. The trace is because the trace, if a faithful semi-finite normal trace exists, it's unique up to rescaling. And so again, modulo these rescalings, which will affect, say, like this maximal value, it's a property of the algebra. Okay.
So, sorry.
Yeah, go
So
ahead.
you said that we were assuming they were faithful, semi-finite, and normal.
Yeah, so I cheated a little bit on this one, so this is not semi-finite.
So we're really assuming throughout the classification that they're faithful and normal, and then if they're semi-finite, it'll be one of the first three, and it's not, then we can put it.
Sure, yeah, we could, well, yeah, I mean, there might be non-semi-finite traces here as well, so really for 4, I should say. I should have written that this trace doesn't exist, basically, there is no faithful semi-finite trace. I wrote it here saying that you could try to write down the trace, like if you did the Hilbert space trace, you would just get infinity on everything. So this was just to emphasize, anything you try, you should just get infinity if it's working as a trace. Okay, so. Okay, a few comments. So in this classification, the types 1 infinity, 2 1, 2 infinity, and type 3 all act on an age which is infinite dimensional. Okay, so all of these have to act on an infinite dimensional Hilbert space. Another thing that's worth remembering is that all of them they're all subalgebras of all of the operators acting on whatever Hilbert space, and this algebra is type 1 infinity. The reason I want to emphasize this is sometimes people have the mistaken impression that these type 2 or type 3 algebras are in some sense bigger than the type 1 algebras. But so this should emphasize that that's not the case, because you always have, for this type 1 infinity, you always have subalgebras of these different types. So that's just useful to keep in mind that there are type 3 subalgebras there. And the way that works is though, so there's some operators inside here that are actually, if you only keep them, would be a type 2 or say a type 2 algebra. It's just if you use this trace defined on that algebra, it's going to be in the type 1 trace on those guys will just blow up on everything. And when you talk about the type 2 subalgebra, you're talking about a different trace than the standard Hilbert space trace. And so that's why the abstract. So in this case, these traces are not the standard Hilbert space traces. They're sort of a rescaled or renormalized version. Okay, and so now there's kind of a useful chart that you can make on some of the properties that these algebras have, just to keep in mind. So we have the type 1, 2, and 3 factors. Switch to
Yeah, so somebody asked, is the Hilbert space always taken to be separable?
so the question is the Hilbert space separable? You don't have to have a separable Hilbert space, but we are always going to assume a separable Hilbert space. So yeah, you want your Hilbert space to have a countable basis. Yeah, so this classification works, I think. If it's not, yeah, if it's not separable, the class, and there might be something funny if. Whether like these properties of semi-finites and uniqueness are non-separable. So let's just say the Hilbert space is separable, yeah. Yeah,
I think one other property which might be relevant in this subalgebra thing is the whether or not the algebra is unitable. As you said, the von Neumann algebra, as you defined it, is unitable.
yeah,
But the von Neumann's original definition of that the algebra is a star algebra, which is weakly closed under the weakly operator topology is only equivalent to that if you assume that it's unitable.
okay.
So, for example, some of the algebras in your paper where you project them down don't include the identity. Well, that's skipping steps, but there's a distinction to be made where the maximal operator, where the operator with maximal trace in any of these algebras is the actual identity in the Hilbert space, and
Okay.
whether it is some finite, some subproject.
Okay, yeah, so the double commutant definition will give you the identity. But if you want to prove that this is same as
Yeah.
weakly closed, you have to talk about algebras with identity, okay. That is not a marker, I thought I tested these. The long lines are bad, okay, anyways. Let me try to write down some of these properties. So the first one that in quantum info you usually like to have is this tensor factorization of the Hilbert space. We saw this for the qubits. This is something that only occurs. So by this I mean your algebra is all the operators acting on the first one, and the commutant's all the operators acting on the second one. And this only occurs in the type 1 case. And so for the type 2 and 3 cases, it was not really a sensible tensor factorization. Okay, but what we just argued here was that there is a trace, where here I mean faithful semi-finite normal. And so in the type 1 case, we know we have the Hilbert space trace. And the important thing about type 2 is that you also have a trace, but the trace, any trace you try to define on the type 3 will not be semi-finite.
Can you change 2 to 3 in the last slide?
Oh, yeah, that would be good. As a reminder, that is type 3 there. So whenever you have a trace, you can talk about density matrices. So you can ask if you have operators which you can plug into the trace in order to get expectation values, and those are always available if you have a trace. So again, type 3, there's not a good notion of density matrix. And similarly, if you have density matrices, you can talk about entropies. And so those are also available in the type 1 and 2 case, not in the type 3 case. So here you have to think a little bit about what this entropy means. It has a slightly different interpretation than in the type 1 case, because this trace in the type 2 case is in some sense a renormalized trace. Also in type 3, often people work, we're going to be talking about quantum field theory. Often people try to compute density matrices in quantum field theory. And the sense in which there's no density matrix or trace means that those things are UV divergent in the quantum field theory case. Okay, so what are some things that you always have? I'm going to write it like this. You always have states for your algebras, so you can take expectation values of your operators in different states. As we'll discuss at some point at a later point, you always have what are known as modular operators. I'm going to write it as delta psi, these are modular. Sorry, that's a bit small.
So what's the notation on state? The lower right.
This is just like omega, it's some state.
Okay. And somebody asked an earlier question I didn't mention, but now it's a good time. Just can you define state in the sense that you mean it here?
Yeah, so states are really just, they're like traces. So a state is a map from A to the complex numbers. So a state is a linear functional on the algebra that you think of as taking expectation values.
And it should be positive, right?
Yes, it's positive. So again, on positive operators, it's a positive real number. Okay, so we'll talk about this later, but you always have modular operators as long as your state satisfies the appropriate technical requirements. which we'll discuss when we talk about modular operators, but these are sort of like a replacement when you don't have density matrices. They're sort of a next best thing. And even so here we talked about having entropies. Those aren't available in the type 3 case, but you can always talk about what are known as relative entropies between two states. And again, we'll go over this in a bit, but this is sort of a relative notion of entropy measure. And in all of these cases, the standard example you should think of, so here, the type 1 case you should think of as either like qubits or the harmonic oscillator. The type 3 case you want to think of as quantum field theory subregions. And so the point of these lectures is to argue that in the type 2 case, these are like subregions in already quantum gravity or semiclassical quantum gravity. And the goal is to try to argue for that last point throughout these lectures. Okay, yeah.
For that last example, are you thinking of type 2-1 and type 2 infinity in particular, or just type 2?
Yeah, we'll talk about both. Depending on the context. Okay. Sorry. So from here, I want to move on to some of the standard constructions of these type 2 and type 3 algebras, because in general, they're sometimes unfamiliar, but there are simple constructions, somewhat simple constructions of these algebras that give you a sense of why certain properties are failing for these algebras. So I'll call this qubit constructions. Okay, so what we're going to do here is return to this 2-qubit example, and instead we're going to take, so here we had sort of two, these were independent qubits, and for a state, instead of working with states written in this usual way, we're going to reinterpret every state as a matrix by just kind of flipping the second qubit around. This is just a rewriting, so all of the set of 2x2 matrices can be equivalently interpreted as 2 qubits. You have this Hilbert Schmidt SMIDT inner product. So where you say, now you say any 2x2 matrix, you can take the inner product like this, where so it ends like a 2x2 matrix that I can consider it as a vector. I can just write trace of m dagger n, where this is just the 2x2 trace on these matrices. This defines a Hilbert space inner product on the set of 2x2 matrices. So in this description, the algebra acting on the first qubit that we talked about, A is just left multiplication. So you say A acting on M is just the matrix A times M. And so then A prime is going to be right multiplication. And so here you'll take A prime acting on M. We'll write it as M A transpose. And I guess I'm going to leave it as an exercise, but the transpose is so that things compose the correct way. When you multiply on the right, you sort of flip the order of composition. So I'll let you think through why there should be a transpose there. Okay, so this is just a rewriting of that 2-qubit algebra in terms of So obviously left and right multiplication will commute, and so that's how you see those algebras are commutants of each other. So you can get density matrices now. So we have some state where M again is a 2x2 matrix, and we want to get a density matrix for the algebra. So we need to find an operator such that trace row A is equal to the expectation value of A. So this means really that this is M acting on AM, which is equal to trace in the 2x2 case of M dagger A M. Oops. Okay, and then you use this 2x2 cyclicity and see that this is really trace of M dagger A. So all I'm saying is when you have a state like this, your density matrix row is just the matrix M dagger. And it's the thing, if you plug it into this equation, you'll reproduce expectation values. So roughly, this is the usual picture where you write the state as kind of, it should look like, this is similar to rho being like psi. Okay, I'm not going to keep that on the board, but that's okay. So just keep that in mind for the density matrix. So now we want to consider a maximally entangled state. So we'll write that as V, just 1 over root 2 times 0, 0 plus 1, 1. Okay, the density matrix by this formula is just this maximally mixed density matrix. So this is just some sort of maximally entangled qubit. And so the goal for constructing these other typed algebras is we want to, in some sense, take an infinite tensor product of these maximally entangled qubit algebras. And what we'll see is that taking that infinite tensor product usually requires you to specify a particular state that you're taking the infinite tensor product in. So we're going to try to construct a state that's sort of a tensor product of maximally entangled qubits and construct an algebra that comes from the limit of that. And we'll see that that's one of these interesting non-type 1 algebras. So let's just state in words what we're this construction. So yeah, so what I was saying is we want to consider an infinite tensor product of A, we'll call this A2, just to remind you that's just the 2x2 matrices acting on the left. And if we took a literal tensor product of, say, all of these Hilbert spaces, you're going to get something that's too big. It's not separable, which was a word that we talked about before. So what you really have to do is sort of take it as a limit of finite dimensional algebras. So to construct the Hilbert space, instead of just taking an arbitrary tensor product, we want to consider states that are of the form M1, M2, up to a certain point, but after a certain point, they have the same state on every factor here. So you want to consider the kind of a vacuum state that's the tensor product of all of the maximally mixed qubits, and then you want to just change finitely many and build your Hilbert space up by taking sort of a limit of where you've only changed 1 and then you've only changed 2, etc. This is a way to get countable a Hilbert space with a countable basis in the limit. So doing this construction will define a Hilbert space that's called a pre-Hilbert space. So it won't necessarily be complete. So you first set up all of these subspaces where you have finitely many that are different from this maximally mixed state. And then you take a completion. So you add limits in this Hilbert space. And so that the, overall inner product is complete.
At what
So-
point do you take the limits? Whenever you finitely many.
So you sort of take the union of. You have the M1, so you can do H1 would be like M1 tensor V. And then H2 would be M1, M2 tensor. So then you'll take like the union of all of these things, and then you have to add limit points basically. So you call this completion by this procedure, we'll call it H infinity V. Okay. That's the notation I want to use, yeah, HV infinity.
One second, can I ask?
Yeah,
I guess when you say limit points, it's limit in some notion of convergence that involves.
yeah, let me see, let me restate it, so. You start with the set of things where only finitely many are different from the vacuum. And then you have an inner product on that space. This is a pre-Hilbert space because it doesn't necessarily contain limits of Cauchy sequences. So you already have the inner product, but you could form things that are getting very close together, but there's not actually, it's roughly a fall off type condition. So there's going to be something that's not, it's falling off as n goes to infinity, but it's never actually going to be V. And so those are the types of things that you add from this limiting procedure.
And you use the.
You use the
product
number-
that you got just from each of the factors.
Yeah, because these are all going to be normalized, so yeah. Okay, so the algebra is going to be constructed similarly. So say we're talking about the algebra acting on the left here. We want to consider operators that are just the same, that are identity in all but finitely many places. So eventually the operator just becomes the identity. So this will define a set of operators acting on this Hilbert space. It'll also act on the completion. And essentially what you want to do is close the algebra in this Hilbert space that you've constructed. So there's this weak topology that comes from taking matrix elements of these operators in this Hilbert space. And so you do this closure. Alternatively, you say, start with this algebra, do this double commutant of it acting on this Hilbert space. That'll tell you certain operators that you're supposed to add in the limit. It's some condition on how the operator is falling off to become the identity. And that will give you a von Neumann algebra. And this is kind of a famous von Neumann algebra. So this is called a type. So this, so close to a von Neumann algebra. And this gives you the type 2-1, what's known as a hyperfinite factor. Okay, so we'll talk about the type 2 property in a second. This hyperfinite distinction will come up a bit in these lectures. It means it's an algebra that can be approximated by finite dimensional von Neumann algebras. And that was kind of put in by construction. We kind of constructed it as a limit of these finite dimensional algebras acting on finitely many qubits. So that distinction is useful. Is a useful distinction when you talk about classifying some of these algebras.
Are there cases we'll consider where there are type 2 infinity hyperfinite factors?
Yeah, so there's always going to be this hyperfinite, just always means you can realize it as a sequence of finite dimensional things. And so all of the types we'll talk about have a hyperfinite version. And then there are non-hyperfinite algebras, which we can maybe talk about after or something. It's not like they're not relevant, but at least for what we're doing, they won't show up. And the classifications that people know of these algebras is not so complete with the non-hyperfinite factors. So one of the important things that this construction does is it shows you that this algebra is an algebra with a maximal entropy state. And it's just this vacuum state that we started with. So we would say that M max is just equal to this it's the one where you just take the maximally entangled qubit on every site. That's going to give you a state for this algebra that's a maximal entropy state. Yeah, and it's important also that this is a tracial state. So if you take expectation values of two operators in this state, you want to remember, so basically the density matrix, you can write this expectation value as a product of the expectation value on every site. So this is going to be a product of the 2x2 trace on each site of this V dagger AI VI V. Remember this V was this V is essentially 1/√2 times the identity matrix. So since the V is the identity, you can just kind of pass it through here. So you can write this as AI VV dagger EI. And then we use cyclicity. So then you write that as V dagger VI AI V, which is equal to the same thing with the operators reversed. Okay, so this is this statement that taking the expectation value in this maximal entropy state defines a trace on your algebra. Yeah, so we're getting this close. Okay, so let me finish talking about this. Yeah, so you can ask what is, so in particular, yeah, so I can define trace of A is equal to the expectation value in the maximal entropy state. And what does this trace actually look like? You can kind of see that it's some sort of rescaled version of the normal Hilbert space trace. So remember, this state was the one where we had this identity state on each tensor factor. So in the finite dimensional Hilbert space, say for n dimensions, it would look like this row. It would basically look like the 2x2 density matrix. So row 2, and n factors. Row 2. So each of these are like 1/2 times the identity. So this is like 1/2 to the n times the identity. But basically this trace is defined so that trace of the identity is actually 1. So basically this trace on the type 2 algebra, you can kind of think of it as something that rescales the trace. They do this in the right way. Well, yeah. So if the density matrix is like 1/, Well, you want this density matrix B to actually be the identity, so you rescale rho by 2 to the n, which means trace is like 1 over 2 to the n. Times the trace of the Hilbert space trace. In a limiting sense. So, okay, all I'm trying to say is that you should think of this trace defined here as somehow an infinitely rescaled trace of the limit of the Hilbert space trace on finitely many factors here. And so that's a sense in which it's kind of the Hilbert space trace, but it's really a rescaled version. Okay, it looks like I think I'm at time for the first lecture. Okay, so this is an okay stopping point. Probably the next time I did want to explain the generalization of this to type 3 factors. So this was the type 2 instruction, and then we'll talk a bit more about modular theory and other things there. Okay, but this is a good stopping point, and then we can do discussion and questions.
Great.
There were a few people who asked to re-ask the questions again.
So will they, do you know who they are?
Yes. Let's see. So Ricardo Espindola had a question.
Yeah, do you guys want to call on people or tell them?
Yeah,
I think you have to do the unmute, but so yeah, I don't know if they can hear you. Probably.
try asking them to unmute and let's see if that works. Or you could unmute them.
Yeah.
Okay, so yeah, we're doing for people online, we're gonna do questions where we'll have the moderators tell you to unmute if you have your hand raised, or have a,
Or you asked a Q.
or you ask a question. And maybe they can say the name too.
Okay, yeah, so Ricardo Espindola, do you want to unmute and ask your question? I don't know if they can hear me or if I'm too far away.
They should be able to if we're not muted. We're not, because I can hear again. Ricardo. Let's see.
Did you guys?
Oh, there it is. Ask to unmute. You can click it.
Okay, thank you. Yeah, my question is about the scattering states. Are scattering states described by type 1 or type 1 finite or type 1 infinity phenomenon algebra?
You mean like in like standard the S matrix and quantum field theory? Is that the question?
Yeah, for example, when you define an S matrix.
Yeah, okay, this is probably a good point to bring up. We'll probably talk about it later, but in quantum field theory, you generally start with there's like a global Hilbert space construction, and this global Hilbert space is the operators that are acting on it is a type 1 algebra. So you want to think of like the full system as being type 1. But in quantum field theory, when we say there's type 3, that's really when you're talking about localized states. So or localized operators. So you'll have operators that are localized in space-time. You want the full algebra of operators localized there. Those algebras are the ones that are type 3. So if all you're interested in is in sort of scattering theories or correlation functions, there's usually a global Hilbert space where you can compute those things in it. Yeah, so let me know if that made sense.
Yeah, that makes sense.
Okay.
And also, whenever you have a Hamiltonian, is there any relation between the type of the algebra and the spectrum? Like type 1, you usually expect a finite spectrum and infinite spectrum, something like that.
So a priori, the actual Hamiltonian of the system won't necessarily affect the type of the algebra. It might, say if it has a continuous spectrum, you probably need an infinite dimensional Hilbert space. But we saw that there were examples of, there's a type 1 algebra that acts on infinite dimensions, there's type 2 and type 3 as well. What we'll talk a bit about when we do modular theory is that there are modular Hamiltonians that you can analyze, and there the spectra of the modular Hamiltonians, as specifically in the type 3 case, it leads to a sub-classification of the types. And so there's certain things like, if you know that all of your modular Hamiltonians have a continuous spectrum, The only way that can happen is in these type 3-1 algebras that show up in quantum field theory. So, yeah, so, but a priori, the Hamiltonian of the system is more like the dynamics, whereas the von Neumann algebra is a bit more underlying, it's more of the kinematic setup that you're doing things in.
All right.
Follow up on the scattering question.
Yeah.
So there's, recent work involving asymptotically flat space-time scattering that indicates that there isn't really a single Hilbert space that all of the states you're interested in fit into.
Yeah.
So, and there the answer is, well, you can formulate the theory just algebraically, but everything you've done is based on a Hilbert space, right?
Yeah.
So is there an algebraic version of everything you've done today, or are we committed to a single Hilbert space in this whole story?
Okay. I thought you were gonna ask something different, but maybe I can answer the statement about there being these different Hilbert spaces. Roughly, I think you should think of that as that there is an algebra, and usually those algebras are not necessarily von Neumann algebras. So now from what I was discussing today, I told you that von Neumann algebras always have a Hilbert space. So this relates to the question you asked, is there an abstract definition of a von Neumann algebra? The answer is yes. They're called W star algebras. So that, and roughly what it is it's like an algebra that has a preferred set of states associated with it. The technical definition is that it's a C star algebra, which we haven't defined, but it's a type of algebra that also is the dual space of some Van X space. And that space is called a pre-dual, and you should think of that as the preferred states, this preferred class of states on your algebra. And so what happens is if you take a state from that pre-dual and you construct a Hilbert space using a GNS representation. So given an abstract algebraic state, you can construct a Hilbert space using a standard construction. You always get a von Neumann algebra that's isomorphic to this W star algebra from that construction. In the things where you have different unitarily and equivalent representations, usually you don't start with a von Neumann algebra, you have something. So you have a C star algebra, which is not, a W star algebra. And so when you do this construction where you take a state and then you construct the von Neumann algebra, you can end up with different von Neumann algebras because that construction will tend to enlarge the original thing. And so that's how you can see that there's different representations sometimes when you do these C star algebras. So maybe towards the end of the course, when we start talking about some future directions, this is one of the things. It comes up in Witten's recent discussion on background independent algebras in quantum gravity. And it's also important in these, scattering in asymptotically flat space as well. So maybe we can discuss that towards the end of the course. Yeah. Yeah.
I think one thing about that is also that that this has been a subject of controversy in the algebraic quantum field theory community, whether or not to call the algebras whether or not to treat the algebras of local subregions as C star algebras or W star algebras. In that setup that you just mentioned, where you take a C star algebra instead of a von Neumann algebra and close it depending on the sector, depending on the scattering sector. I think the local algebras are all still, well, for conventional theories, if you follow like a conventional formalism, they would all be W star algebras. But you take a union of them, a C star union of them at infinity. And then when you close that, depending on the sector, you get different type 1 algebras.
Well, yeah, let me say something on that. So usually one approach to one of the algebraic approaches does normally focus more on C star algebras. And there, because there's not a preferred set of state, this is usually where this Hadamard condition for correlation functions comes in. It's essentially trying to answer the question of how do you select a preferred class of states. There's not like a direct correlation between the Hadamard condition and the construction of a von Neumann algebra, but it's sort of, well, it's something that people work on, like what are the conditions you need to select a unique folium of states. But assuming you do that in the local regions, it's true then when you go, assuming you do that correctly, it's expected that local algebras that satisfy these nice conditions are type 3 and that they're essentially, yeah, if you have they have this unique pre-dual associated with them. But then again, when you go out to infinity, you can get other things that can happen. And roughly the way I usually think about that is if you're in like an infinite volume space, you can get different von Neumann algebras in thermal states as opposed to states constructed around the vacuum. And it's usually, if you think of a thermal state in an infinite volume, that has infinite energy relative to the vacuum. So usually when you're getting these different things in the global Hilbert space, it's something like you were working in a thermal state or something like that. I mean, it's not like a theorem, but that's one way to think about what's happening there.
Somebody asked, I'm not sure exactly what they're getting at, but maybe you'll know.
Uh-huh.
Are you sure with your definition of maximally entangled state? I guess there's some ambiguity in the notion of maximally entangled state, or are you just using that as a word to describe that?
So for the finite 2x2 things, you can say has maximal entropy, I guess. I didn't show that was true here, but if you work out density matrices for this algebra, you can also prove that. So this state here is the one that has the identity as the density matrix it's almost by definition, because we're defining the trace as the expectation value in this state. If you want to reproduce the expectation values of this state with the density matrix, you better insert the identity as the density matrix. And then you can compute entropies by doing trace row log row. And so I didn't do it here, but it is true that the maximal value of that entropy functional is actually 0 in this case, and it's for this state. And so really, again, the fact that the entropy is 0 and that's maximum, so all entropies are negative, is related to this rescaling that we did for the trace. So really, this is like a vacuum subtracted entropy. And so we have a maximal entropy state, and the entropy we compute is we subtract off that vacuum entropy and compute entropies of all the other states. All of the other states have less entropy. So this entropy functional would be negative there. So yeah, that's, like I said, we didn't prove that here, but you can prove that there is a maximal entropy state.
And then underneath that, we talk about this max entropy state producing a trace. Is there general importance, significance to being able to make a trace from a state? I guess those two words together.
Oh yeah, so I mean, you can kind of think of, if you think of us, okay, so there's like vector states that we were talking about here.
Yeah.
But then you can think of this more general notion of a state as just giving you expectation values. So that's more like that. And so traces are like states because they take your operators and give you some expectation value, which is the trace of the operator. So that's the sense in which traces are kind of like states. Depending on, states also have a normalization condition. So depending on which type you're in, the trace might not be normalized, but apart from a normalization, a trace is like a state. And so that's kind of why it works. So anytime you have a trace where this tracial property, or anytime you have a state that satisfies this tracial property, the expectation value in that state is a trace. And so that's one way to think of what traces are. Yeah. You too.
Yeah, so Krishna, I think was looking for some clarification on the construction of the type 2 algebra. Maybe they can unmute and now say that.
Did you click on, or probably have to click on them?
I don't know if I left people in a state of involuntary muting.
I can click ask them.
Yeah, see if that works.
Hi, am I audible?
Yes, we can hear you.
So I just wanted to clarify, how did you construct the Hilbert space, and then how did you conclude that it's a type 2-1 algebra acting on it? Just to sum it.
Yeah, sorry. Yeah, let me review. So the Hilbert space, I erased it, but we started with this infinite. We started with like a vacuum state, which we said was the tensor product of this V on infinitely many sites. Then we constructed some states by just changing finitely many of those. This was a pre-Hilbert space, so there's an inner product on those states. And and then you have to do a completion. So you add sort of limits of Cauchy sequences, and that defines a completed Hilbert space that your operators can now act on. The way that you got that it was type 2 is that we found a trace on the algebra. So it's good that you asked this, because this is one of the ways that you can diagnose what type your algebra is if you can just find a trace on the algebra, you know you're in this type 1 or 2 case. So we just checked that if you take the expectation value in this maximal entropy state, that it satisfies this tracial property that expectation value of AB is equal to expectation value of BA. That says it's not type 3. I didn't prove that it's not type 1, but the way you do that is you would have to find operators you would have to show that you can get a continuum of values for this. So maybe let's call that an exercise. I'm sure you could do it, but yeah. And then you also have to check, we essentially took the trace of the identity. So if we take the identity and insert it here, we get 1. And so that means it's a type 2-1 and not 2 infinity.
Abhay Ashtikar has a question. Abhay, can you speak?
Yeah, I general question about, I mean, you several times mentioned quantum field theory.
Yeah.
But also these algebras are, of course, one Neumann algebra is in particular C-star algebras, so they're all bounded operators. And so do you have in mind, I mean, so these are not really the usual smeared operators that we, consider in quantum field theory, like the field smeared on some open region.
Yeah.
So these are the only algebras I know of would be Weil algebras.
Yeah, but those are when you do the Weil algebras there, you're taking basically bounded functions of your smeared fields, right? So that's how you get a C-star algebra from the
And so you could consider one Neumann algebra like that. But is there any other way to do it in field theory than Weil algebras? Do you know any other examples you know of?
What do you mean any other way? So normally,
I mean, I just have these local field operators, and I'm going to consider smeared versions of them. Those are the usual operators. And now, as you said, Weil algebra, exponentiates them and makes them bounded.
So I guess Weil algebra assumes some sort of free field canonical commutation relations, right? But say you had a CFT where you do have just, we'll talk about this a bit more in a later lecture, but you do have you have correlation functions normally in a CFT, which you think of as operators valued at points. So you take smearings of those operators, and then you do the same thing where you take bounded functions, and that's what you're supposed to, in principle, that's really the von Neumann algebras. In practice, you often work with the unbounded operators as well. And you just have to be careful not to get in trouble with issues with domains. But usually you can do a pretty good job just with those.
But everything, I mean, from where to go, everything was bounded. I mean, you're using right and left. So how can you not get into trouble with unbounded operators? I mean, nothing is well defined. Trace is not, I mean, absolutely nothing is well defined, right? Products are not well defined.
The way it works is you start with the von Neumann algebra, and then there's a whole story of where you talk about operators affiliated with your von Neumann algebra. So you consider unbounded operators that still commute with with your von Neumann algebra within the domain that they're defined. And then these are unbounded operators affiliated with the commutant. And so there's sort of a story there of how to deal with unbounded operators that are affiliated with your algebra. We're not going to go into too much detail, I guess, about that. I'm probably not the expert on it, but there is just a way to translate between the von Neumann algebras and the operators we normally think about, which are usually unbounded. I don't know if that's satisfactory, but there is some connection. Yeah.
Okay, but the last question was, but I mean, if I look at quantum field theory that I'm interested in, rather than, I mean, physically interested in, rather than something that is mathematically solvable, then in 4 dimensions, we don't really have any exact quantum field theory that is solvable, right? So,
well, we have free field theories, and actually, you
can
do it. A lot of the stuff that you want to do in gravity is interesting, even at the level of free field theories.
So that was really my question. So, but that really is really restricted to free field theory, right? It is not, I mean, can we consider in that gravity context or later, anything that is interactive? And if you do, then it is going to be perturbative. And can any of these things make sense order by order or anything like that? Or
yeah, so okay. So one thing that you do is with the algebraic quantum field theory stuff is you try to write down very general axioms, things like if you're in flat space, you want to have representations of the Lorentz group, you have axioms associated with causality. And these are things that you really just expect a Lorentz invariant theory to satisfy. And then you try to prove things about an algebra, assuming those very, basic assumptions on causality or something like that. And so then you would say, if you ever wrote down an interacting theory that satisfies these axioms, you can just assume that it'll have the right properties. So for example, maybe n equals 4 super Yang mills is maybe the best candidate to have like an interacting non-perturbatively defined theory. So it should satisfy these basic axioms there. The second thing you said is though more about order by order and perturbation theory, and even on that line, you can ask about effective field theory and how that fits into this. And that's maybe a good question. It's not like, say, I think you have a non-renormalizable effective theory. I'm not exactly sure how it fits into the von Neumann algebra language, but you do have to try to make sense of that sort of formal perturbation theory.
Okay, so just the bottom line is that for gravitational context, the matter fields implicitly is really being assumed to be linear fields, non-interacting fields. Is that right?
I guess I won't explicitly assume it, but I'm not saying, I'm gonna try to write down general things that will hold if you were able to do the interacting fields in curved space-time.
Okay.
But if you want to have a model, just have a model in mind of free fields, and there's still interesting things there.
Okay, thank you.
There's a question I can ask for another participant. Could you explain why the algebra of bounded operators on Hilbert space is type 1 infinity? You said it is.
Oh,
but he didn't, and I didn't, or this person didn't, and I didn't catch the reason.
oh, why? So, okay, you have a trace and you have all the 1D, you have the 1D projectors. Yeah, so, okay, first of all, you have the Hilbert space trace. And then you also have operators of the form, E2 is like 1, 1 plus 2, 2. So you explicitly construct these projectors that you know that the trace, trace of E1. Yeah, then you have to assume you have to prove there's nothing in between, I guess. So yeah, I didn't exactly prove that. Yeah, so in the von Neumann classification, it's not actually done necessarily in terms of traces. I use the trace as something that's I think a bit easier to understand what's going on with these algebras. Normally, the standard presentation looks at all of the possible projectors that are in your algebra. They have an order defined on it. So essentially there's a partial order on these projections, and then you try to prove properties about this order of projections. And in that case, there's a notion of a minimal projection, and that's things like this. These 1D projections are known as minimal projections. You can't get something that's sort of smaller than this. And essentially, if you can prove your algebra has something like a 1D projector, it has to be type 1. So probably that's more like how it works. So you have to prove that all of the bounded operators is a factor, and then you show that it has a minimal projector, and then that proves that it's this type 1. But yeah, I guess I didn't prove it. I just told you that that's what it is.
All it has to have is one minimal projector.
If you know it's a factor, and then you see that it has one minimal projector, you need to show that it's a minimal projector. So you have to understand what this partial order on projections do. Yeah. So, and then, I mean, the type 1 infinity, it has all of these guys, and then it has a bunch of other projectors that you call infinite. And they can kind of be arbitrarily subdivided, it's just all of their traces are infinite. But these are things like, you know, you're working standard quantum mechanics, you're working with L2 of R. Okay, you're doing quantum mechanics on the line. You have things like, how do I want to write this? RAB of Q hat, where RAB is just this function. You know, it's 0, 1, A, B. You just have some sort of top hat function. This is a projector. If you just multiply it with itself, you get it back. And if you try to compute that, the Hilbert space trace of that, you'll get infinity. It's roughly, you do it in the position basis, and you're going to get kind of an integral over AB of delta of 0. And so this is in that algebra. It's an infinite projection, so you assign infinity to it, and so you have all of these funny projections. They just have all have infinite trace in this case. So I think this is a useful thing to keep in mind, to remember that there are operators you're used to that say you could maybe use operators like this if you wanted to construct like a type 2 or a type 3 subalgebras. So they would have features like this that the standard Hilbert space trace blows up on them. Okay. Yep.
I think one thing related to that is that it's not just a partial order on the projectors that exist. It's like a partial order which you can quotient to a total order by identifying all the projectors with the same trace. You just get like an enumeration.
You identify all the, sure. Okay.
Yeah, so it's very strong for a part. It's very close to a total order. It's like you can enumerate them in order with certain numbers.